Alright, should be live. Studying. Alright, so sound should be good. And we're watching this person's YouTube channel because they did the notes for what I need to study. They went over it, so we need to open up chapter 3. Need to open up chapter 4 and then this one. I've been studying for this all week. I'm nervous as hell. And yep, pretty much sums up everything. Do 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 do. It's gonna be a long stream today. This load. Alright. So let me load up these videos. We got this one, this one, this one, and this one. And then she skips over some notes, so I'm gonna have to follow along with that. But this is for chapter 3, so we might as well start with the beginning again. I think going through this, I've watched these videos, I think, some of them twice. This will be my third time watching this one.
Then the host receives the UDP with the
No.
segment. So with the now let's understand more. With the port numbers assigned to the UDP sockets, we can
Alright, go back to the beginning. Do 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 do. I would download the slides, but I don't feel like it. Hold on.
Hello everyone. So this is week 4. We are going to start with another new chapter, which is chapter 3, and we are going to start with another layer of the TCP/IP model, which is the transport layer. As I discussed in
From what I know, transport layer has internet protocols, and two of them are TCP and UDP. TCP is connection based, UDP is connectionless. Uh, UDP is user datagram protocol, TCP is transmission. It's a transmission cost protocol, I think. Uh, there's no handshaking on UDP. UDP is, was it believe one round trip time. What else do I know about UDP? Something about no frails. I don't know. I believe UDP guarantees, uh, mm, guarantees, I think, delivery. It has, uh, in order delivery, but it doesn't guarantee in order delivery. Trying to think, what else does UDP have? It has security. And then TCP, well, both of them have, uh, is it multiplexing and demultiplexing? That basically is like the source and destination thing with the IP addresses, and the ports. For the, what was it? For UDP, I believe all you need is destination ports, destination IP, and destination port. Uh, and then for TCP, you need both, was it destination and source? Or sender and receiver? Oh yeah, there's another thing. TCP has a sender. Sender goes to the network layer, and then receiver goes to, I believe, the application layer. So what else? What else can I say about them? I feel like I'm missing a lot more. Believe that's mostly from chapter 3 though. What else do I know about TCP? TCP. There's handshaking because it's. I believe uh, the the datagram is 32 bits. Uh, I don't know how deep that I need to know about that, but we'll just continue.
In my previous lecture that we are going to follow the top-down approach, discussing each and every layer in detail. In my previous lecture last week we discussed about the application layer in detail. What are the applications and what are the protocols related to that layer. So this week we are going to start with the transport layer. In this chapter we are going to understand
Yeah, there. Congestion control. Okay, TCP
the
congestion.
principle.
Oh yeah, congestion control also has, was it the flow control? But that's in chapter 4, I think. Flow control, and then there's like a buffer for the input and output, so it doesn't lose packets. So because if it overflows, then you can lose packets. But I think chapter 4 is mainly just about TCP. Then I'll have to.
Behind the transport layer services, we have already learned that the two important protocols of the transport layer are UDP and TCP. So we are going to learn more about these protocols. So these are the topics that we are going to cover in this chapter: transport layer services, multiplexing, demultiplexing, UDP, principles of reliable data transfer. I have divided my lecture into two parts. So in the first part I am going to cover until principles of reliable data transfer, and in the second part I will cover the rest of the chapter. So let's start
These notes I think are from like
with this chapter.
2 years, 3 years ago. Even though the video says last year, but this is, I think it said version 8 or version 6, and then we're on version 8. Um, but the notes are pretty similar, so that's why I'm following along.
Let's
Because it's a lot easier than me just reading the notes and trying to memorize it. If I can hear someone say it, I think I can memorize it better and follow along, which is the whole point of going to class, but this class is so boring.
first of all just talk about transport layer services and the protocols. So
Yeah, their sender breaks up, so transport protocols run in each end systems. Send breaks into segments. Oh, and that's another thing. One of them, logical communication between applications process running on. Yeah, there's two different types of communications. One is like network layer is on hosts, and application layer is on processes, I believe. Not to see.
So transport layer actually provides the logical communication between the application processes which are running on different hosts. What do we mean by logical communication? We mean the meaning of logical communication is that from an application's point of view, It looks like if the hosts running the processes were directly connected. That means the machines which are running the processes, they are directly connected. It looks like from the application's point of view, just like for example when you are using any application layer protocol, for example HTTP or even messengers, it seems like to you that you are directly connected to the receiver or to your friend. So this is what we mean by the logical communication. But in reality, the host may be on the opposite side of the planet. Of course, it's true, it's a reality. For example, you are trying to browse Berkeley University page. It's not here, the Berkeley University server, it's not in the Saudi Arabia, it will be somewhere in USA. So when you try to browse that page, to you it looks like that the host, the machine to which you are connected or to the application which you are connected, it's quite near to you, but actually it can be on the other side of the planet, and it is connected through many routers and many types of link. Application processes use the logical communication provided by the transport layer to send the messages to each other, and they are free from the worry of the underlying architecture or the physical infrastructure. Now, if you see in this figure, here in this figure, we have the devices connected to the routers. Transport layer protocols are implemented in the end system. So transport layer protocols, they are implemented in the hosts. They are not implemented in the network core or the intermediate devices. Transport layer protocols are not implemented in these routers. On the sending side, the transport layer, so on the sender, at the sender side, the transport layer converts the messages it receives from the application into the transport layer packets, which are called as segments. We learned about it in the chapter 1. And in the receiver side, it reassembles the segments into the messages and then passes it to the application layer. So more than one protocol, more than one transport protocol is available to the applications, and we have two protocols which are TCP and UDP.
TCP and UDP, and that's basically what this entire chapter is about.
Alright, so moving ahead, so this is logical end-to-end transportation.
See, like some of the stuff that I have in my notes don't match there, but the main concept is here. Network is host, transport, what did I say? Yeah, network is host, transport is processes. How I'm trying to remember this is transport has a P in it, processes. Yeah.
Okay, let's understand the relationship between transport layer and the network layer. We know that the network layer is below the transport layer. Transport layer lies above the network layer in the protocol stack, and the transport layer provides logical communication between the processes running on different hosts. Now, a network layer protocol, it provides logical communication between the hosts. So it provides logical communication between the hosts, whereas transport layer provides logical communication between the processes. Processes are nothing but your application. So transport layer.
And that's the thing, because wait. Network layer goes to... Wait, confused now, hold on. Yes, oh, okay. Yeah, I'm confusing this. So logical communication between...
relies on reliable and enhanced network layer services. So it relies on the network layer services. Let's consider an example over here, which is given in your book. Let's assume that
this example's not worth it.
living on coastal 44Y, all her east coast part of the stations are quite good uh, in the last
So I think, let me see here. Yeah, so it skips over this, so let's look at this for a second. Sender is passed an application layer message, determine segment. So sender is passed an application layer message, which is here. And sender's inside the transport, sender, receiver, between processes. And I believe, wasn't processes, passes to the network layer, determines segment header fields, creates segment, passes segment. So this, I would say, like, it's not demultiplexing, but it feels like it. Receives segment from IP, check header files, extract. Yeah, it is multiplexing and demultiplexing. Yeah, demultiplexes message up to, yeah, it is. So that's basically just, okay.
uh, we talk about internet transport layer protocol. So in the last week we learned about that the two important transport layer protocols are TCP and UDP. TCP is a connection oriented reliable protocol, whereas UDP is a connectionless unreliable protocol. So TCP is reliable in order delivery. It has congestion control, flow control, connection setup. So connection setup is required, whereas UDP is unreliable.
Alright, so unreliable, no frill extension of best effort IP. I'm definitely gonna remember the no frills part, but not the other. TCP transmission, it's transmission control. I thought it's cost. Transmission control protocol, reliable and order delivery, congestion control, flow control. It's because it's a connection based setup. That's why it's reliable. UDP being unreliable is unordered delivery, no frills extension. Service is not guaranteed or not available. Delay guarantees and bandwidth guarantees.
It's a connectionless, it's unordered. Services not available with these are delay guarantees and the bandwidth guarantee. Uh, these are not available with these protocols. Now let's talk about important concept of multiplexing and demultiplexing at the transport layer. So as we know, multiplexing, you might have learned the term multiplexing in your digital logic also, many to one, and demultiplexing is one to many. Alright, so what is multiplexing and what is demultiplexing in terms of transport layer and how it is done? First of all, let's understand what is multiplexing. Multiplexing means gathering data from multiple sockets, from multiple applications, enveloping data with header and which can be later used for the demultiplexing. Let's understand more about this multiplexing and demultiplexing. Alright, now we have some diagram over here. The yellow part represents the socket and the blue circle represents the process. So multiplexing means gathering data from multiple sockets or from multiple applications, enveloping data with the header which can be later used with the demultiplexing. So let's understand how it happens. How now multiplexing occurs at the source host and demultiplexing always occurs at the receiving host. So always keep in mind, transport layer has the responsibility of delivering the data delivering the data in the form of segments to the appropriate application process running on the host. So let's take an example. You are using a computer and you are using downloading some web pages while you are running a FTP session also and two telnet session also. So when you are downloading a web page, that means you are using HTTP, right? Apart from HTTP, at the same time you are running FTP session also, and you are using two telnet sessions also. So you have now four application processes which are running, two telnet processes, one FTP and one HTTP process. So now when the transport layer of your computer receives data from the network layer, so when the transport layer receives the data from the network layer, it needs to direct the received data to one of these four processes, right? So how it is done? Because the data which is received from the network layer by the transport layer, it should be directed to the correct application for the application for which the data is meant. So let's see how it is done. Now a process can have one or more sockets. We understood the sockets in the previous lecture also. Sockets are just like the doors from where the data passes from the network, and through which the data passes from the process to the network. It enters into your system and it leaves your system, right? So if you see over here, we have a socket over here. So the transport layer in the receiving host does not actually deliver data in the receiving host. So when it is received, for example here, it is not delivered directly to a process, but it is delivered to the socket, because at any given time there can be one or more socket in the receiving host, and each socket has a unique identifier. So the format of the identifier depends whether the socket is a UDP or a TCP. So let's consider how a host, the receiving host will direct the incoming transport layer segment to the appropriate segment. Now each transport layer has a set of fields in the segment which have identifiers for this purpose. So at the receiver side, what happens? The transport layer will examine those fields. So transport layer will examine those fields, will examine that segment to identify the receiving socket number, and then it will direct that segment to that particular socket number. So this job of delivering the data in a transport layer segment to the correct socket is called as the demultiplexing. So the job of gathering data chunks at the source host will be later used for demultiplexing to create segments, and it passes these segments to the network layer is called multiplexing. Now transport layer is a middle host. So demultiplexing segments arrive from the network layer, and this is done by directing the arriving segments to the corresponding process socket. So if you see in this figure, host 1 using some process 3 is trying to send a packet to host 2 to the process 1, and over here the host 3 is using process 4 is trying to send a packet to process 2 on the host layer. So transport layer is a middle layer over here, or the middle host in the host number 2. So when the packet arrives at host 2, transport layer should demultiplex the segment which it gets from the network layer. Now after demultiplexing, it will direct the segment either to the process 1 or to the process 2 by checking the socket number provided in the arriving segment. So when the segment arrives at the transport layer, it checks the socket number. So based on the socket number, it directs the message to that particular application, because the processes have different socket numbers. Okay, so multiplexing occurs at the sending side, whereas demultiplexing occurs at the receiving side. Alright, moving ahead. How the demultiplexing works. Now, host receives IP datagrams. We have learned in chapter 1, network layer receives datagrams, transport layer
32 bits.
receives segment. Demultiplexing always occurs at the receiver side. So host will receive the message in the form of the datagram. Each datagram has the source IP address and the destination IP address, and each datagram carries one transport layer segment, and each segment has a source destination port number, which we call as the socket number. So socket number is the combination of the IP address and the port number. So host uses IP address and port number combined together to direct the segment to the appropriate socket. Socket number of every application is the combination of the IP address and the corresponding port number. So let's understand how these are created. So connectionless demultiplexing. So how we can create with the programming. So datagram socket package, by using this package, we call it as the socket programming in Java. These are just for your information, the lines of code. We create an object of the datagram socket and we provide over here the port number. So this is another socket created and we provide some port number over here. So when a UDP packet is created in this manner, we are creating a UDP packet over here. When it is created in this manner, the transport layer automatically assigns a port number to the socket. So a transport layer assigns a port number in the range of 1024 to 6553. The port numbers range from 1024 to 65,535. That is, and it checks a port number or assigns a port number that is not used by any other UDP port in the host. Java program can also create it can make it as empty, or it can provide over here the port number. So specific port number is provided. If you don't provide any port number over here, you keep it empty, then the Java program will, the transport layer will automatically assign the port numbers. Application developer writing the code were implementing the server side of a well-known protocol. Then the developer has to assign the corresponding port number. Now, then the host receives the UDP with the segment. So with the let's understand more. With the port numbers assigned to the UDP sockets, we can now describe the multiplexing and demultiplexing. Let's assume that we have host A and host B. Host A has a port number something, let's assume 19157, and it wants to send an application message to a UDP process to the host B, and let's assume the port number is 46428. So the transport layer in host A will create a segment that will include the message and the source port number, which is 19157, and the destination port number, and the two other values, which will be the IP addresses. And this segment will be passed to the network layer. Network layer will encapsulate the segment in the IP datagram and deliver the segment to the receiving host. Now, when the segment arrives at the receiver side, so the transport layer at the receiver side examines the destination port number. So when it checks the destination port number, when it checks the destination port number, now at that particular point, the host B can be running multiple processes and each having UDP sockets. So UDP segments arrive, host B demultiplexes each segment based on the port number to their correct application. So UDP socket is fully identified by two tuple constraints, which is IP address and the port number, which is always called as the socket address. So when the host receives UDP segment, it always checks for the destination port, and the UDP, it directs the UDP segment to the socket with that port. And IP datagrams with different source addresses, so IP addresses or source port numbers are directed to the same socket. Alright, so moving ahead.
Yeah, I kind of already know most of this. Like, I
So if
remember it.
you see over here, this is the example that we discussed. Okay, so SP here is source port, DP means
Oh, you don't
destination
need
port. So for example, this process P2 wants to send a
the
data
source IP,
message
looks like.
to some
You just need the
host,
ports.
some other host. Let's assume that the IP address is A, the IP address is C, and the IP address is B. So when it sends, creates a data, creates a segment, it mentions the source port and the receiving port. So this is the source port and this is the destination port. So when the segment arrives over here, transport layer checks what is the destination port and it directs the segment to that particular application. Now after receiving the message, let's assume that the process 3 wants to reply to this client on the same process from where it received the application. So when it will send the message, it will put the source port as its own port and the destination port as the port of the process from where it received the message. So it sends the data. When the transport layer receives the segment, it will check for the destination port and directs the segment to that particular process. And same thing happens over here between the other client having the IP address C and B. Alright, so TCP socket is identified by 4 tuple: source IP address, source port number, destination IP address, and destination port number. So socket is identified by 4 things: IP address of the sender, port number of the sender, IP address of the destination, port number of the destination. Receiver host uses all 4 values to direct the segment to the appropriate socket, and the server host may support many simultaneous TCP sockets because server may have many TCP segments or TCP sockets which are carried on at the same time, and each socket will always be identified by the 4 pair of things, which are sender IP address, sender port address, destination IP address, and the destination port address. Alright, web servers, they have different sockets for connecting to the client. Non-persistent HTTP have different sockets for each request. Okay, now let's talk about UDP.
I'm also into computing. Are you taking the same course? I have an exam on Wednesday that I've been trying to study for. This exam basically decides my grade, because right now I have like a CSC 2010. I don't know it. Oh wait, it says 210. I don't know those numbers. Because for my college we do it like in thousands, so I don't know.
Moving ahead. Alright.
Yeah, because my course is 3004 for this class here. So I'm not sure how it correlates. Hold on.
So, UDP, User Datagram Protocol, no frills, bare bones Internet Transport Protocol. It's an Internet Transport Protocol, and it's the faster protocol. It's a connectionless protocol. Best effort service, UDP segment, it provides best effort service, but UDP segments may be lost, may be delivered out of order. Out of order means, suppose there are 10 segments to be delivered, so it may be delivered.
I'm only streaming this, so I don't know. I could stream something. fill up time. I guess sort of like force me force myself to do this, even though I was watching these yesterday and throughout the week. This person, this isn't my professor, but they recorded their lecture, which has helped because most of the week I was studying this until I found this Thursday night, the videos. I was like, oh, I'll just watch the videos and follow along. So much easier than just trying to memorize the notes.
As fourth, first of all, fourth segment is delivered first, then eighth, then two, then one, like this. It is a connectionless protocol. That means there is no connection establishment, no proper connection establishment between the sender and the receiver, which means that there is no handshaking between the sender and the receiver. Each UDP segment is handled independently of others. So let's assume that there are 5 UDP segments need to be sent. Each UDP segment will arrive out of order and it will be handled independently at the receiver side. Now, there is no connection establishment which can add to the delay. There is no connection state at the sender, or the connection state is not stored. Small segment header, and it does not provide congestion control. But then why there is a UDP? Because UDP is a faster protocol and many applications may not require reliable, but sending the data at a faster speed is much more important, like the streaming applications. So that's why there is a need of the UDP protocol. Alright, so moving ahead, our next topic will be the principles of the reliable data transfer. There are many applications which use UDP, especially the streaming and multimedia and internet telephony and network management. Many applications use UDP protocol. We are not going
Is
into.
that what this is? Streaming network? What does this stand for? Simple network management. Okay. That's streaming. Simple. Domain name service. I don't know why they added HTTP here, the 3 here, if they just listed it again down below. So, it's weird.
Much detail for the UDP, like its datagram structure or whatever. Now we will start with the next topic, which is the principles of the reliable data transfer. So what is principle of reliable data transfer? Now in this part, we will actually focus on the problem of the reliable data transfer. That means there should be a reliability in the transferring the data
Yeah,
in general
there,
context.
there should be. Alright, these notes are kind of out of order, so I don't know. So it skips over checksum, but my professor put checksum notes in. So I don't know. I have to ask him on Tuesday about, because I know what does it detect errors in transmitted segment, but I don't know how much I need to know about this. Cause, bro, adding up, doing this, is such a pain. He has interactive problems that I'll do after the video, but it's just adding up this and then doing the ones complement is such a pain unless we're given the binary. I mean, like, I could reverse engineer this, but to a binary, or I mean not binary, it's already binary, to decimal, but it's just why? But it basically skips all that, and then we just do this. No frills, segments, maybe lost. UDP has its pluses, no setup handshaking.
So this is
Alright, hold on, let me go back.
telephony, network management. Many applications use UDP protocol. We are not going into much detail for the UDP, like its datagram structure or whatever. Now we will start with the next topic, which is the principles of the reliable data transfer. So what is principle of reliable data transfer? Now in this part, we will actually focus on the problem of the reliable data transfer. That means there should be a reliability in the transferring the data in general context. So this is actually, you can say this is relevant, since the problem of implementing reliable data transfer not only is at the transport layer but also at the data link layer and the application layer. So it's a general problem of central importance to the networking. So let's first of all understand this. It's an important in all application, and but it's a problem in transport and the link layer. It's one of the top 10 list of important networking topics. So reliability in providing.
Hey, I know this was listed in my notes somewhere, but I don't know if it's like at the end of this, or because this is a whole different topic now.
Providing the data transfer is when you are doing some research. It's one of the important topic, a networking topic. So before we understand this diagram, we must know that it is the responsibility of the reliable data transfer protocol to implement this service, and this task is actually made difficult by the layer below. The reliable data transfer protocol may be unreliable. For example, below the application layer, we have two protocols, TCP and UDP. TCP is a reliable data transfer, and but it is implemented on the top of IP, which is unreliable. So if you see, if we use TCP over here, below the net transport layer, we have a network layer, and the important protocol of the network layer is the IP protocol. IP is highly unreliable protocol. So a TCP, which is a reliable data transfer protocol, is implemented on the top of the unreliable, which is the IP protocol, end-to-end network layer. So we can say that the layer beneath the two reliably communicating endpoints might consist of a physical link, which is the in case of the data link layer, or a global internetwork. So we can view that the lower layer is simply unreliable point-to-point channel, because when the data is sent, the link, the physical link, the path is also not reliable. So we can say that the data, reliable data is actually transferred on the unreliable channel. So we will actually understand this diagram, and we will incrementally develop the sender and receiver sides for the reliable data transfer. So let's understand over here.
Is it only
If you see
for... Oh my god. Was it only for
on the top,
TCP?
TCP and of the reliable data transfer protocol to implement this service, and this task is actually made difficult by the layer below. The reliable data transfer protocol may be unreliable. For example, below the application layer, we have two protocols, TCP and UDP.
Mm-hmm.
TCP is a reliable data transfer, and but it is implemented on the top of IP, which is unreliable. So if you see, if we use TCP over here, below the net transport layer, we have a network layer, and the important protocol of the network layer is the IP protocol. IP is highly unreliable protocol. So a TCP, which is a reliable data transfer protocol, is implemented on the top of the unreliable, which is the IP protocol, end-to-end network layer. So we can say that the layer beneath the two reliably communicating endpoints might consist of a physical link, which is the in case of the data link layer, or a global internetwork. So we can view that the lower layer is simply unreliable point to point channel, because when the data is sent, the link, the physical link, the path is also not reliable. So we can say that the data, reliable data is actually transferred on the unreliable channel. So we will actually understand this diagram, and we will incrementally develop the sender and receiver sides for the reliable data transfer. So let's understand over here. If you see over here, the sending process has the data to send, and it assumes that the channel through which it is sending is reliable. But actually how the service is implemented over here, the sending side of the data transfer protocol. So here the sending side of the data transfer protocol will be invoked from above by a call, by calling this method RDT send. RDT means reliable data transfer protocol. Now it will pass the data to be delivered to the upper layer at the receiver side. So when
Yes, that's the complexity of reliable data transfer protocol will depend strongly on characteristics of the unreliable channel. This is what confuses me, is how this turns into reliable and then this becomes unreliable. Does does it not need to be reliable if this is reliable? I'm not exactly sure what this is saying. Because if it's already reliable, what are we doing? Or wait, is this for back and forth? What's up, David Z playing? Oh no, we can't be having that. How the fuck do I ban you? Bro, I can't ban you in my own chat? That's so fucking lame. Gotta open up chat view, moderator view. How do I... There we go. Oh, why did it show everyone's messages twice? That's weird. Alright. Bro, it says there's like 8 people watching my stream. What? Here, I'm gonna put, oh, I'm not gonna put follower only on, because that's really the first time. But, yeah. Oh well. Hey, but it said they followed, but I don't know if that counts as a follow. Alright. Uh, what was I doing? What was I doing? I don't know who's still watching.
it is sent over here on the unreliable channel, it will be passed to the upper layer at the receiving side. It will be passed at the receiving side. Now on the receiving side, we have RDT receive, so reliable data transfer receive. It will be called when the packet arrives from the receiving side of the channel. So when RDT protocol wants to deliver data to the upper layer, it will do so by
Wait,
calling the deliver from the receiving side of the channel. So when RDT protocol
RD.
wants to deliver data to the upper layer, it will do so by calling the deliver data. If you see over here, deliver data. So we use the terminology packet rather than the transport layer segment over here, because the theory which we are going to develop in this is not just based on the internet transport layer protocol. So the generic term most of the time packet is sent. So characteristics of the unreliable channel will determine the complexity of the reliable data transfer protocol. So the meaning over here, the overall big picture is we have some reliable data transfer to reliable data to send, but the protocols which are operating below the layer or underlying or the physical links may be unreliable.
Alright, I think that, hold on, I missed it. What she just said I think was...
So the meaning over here, the overall big picture is we have some reliable data transfer to reliable data to send, but the protocols which are operating below the layer or underlying or the physical links may be unreliable.
Yeah, because IP is not reliable internet, and then...
Alright, so this is what I explained you right now. So RDT, reliable data to send, which will be called from above, for example, by application, and pass data to deliver the receiver upper layer, right? UDT send is called by the RDT to transfer the packet over the unreliable. So it will be called by the it will be called to send the packet on the unreliable channel. At the receiver side, RDT receive will be called when the packet arrives on the channel, and then deliver data will be called to deliver the data to the upper layer. Alright.
Okay. Why is the...
So let's
Like,
understand.
it completely goes to this image right here, which completely skips over these notes here, which is one day I'm a bit confused about, because, no. Did these later become important after this version 6 to version 8? They're like, oh, you know, maybe we do need to talk about these. No, unless these are just self-explanatory, which acknowledgements are, negative ones are. Sender retransmits packet on receipt of next, stop and waits for the response, obviously. Hold on. Does UDP have reliable data? I don't think so, if it has it, but let me just make sure. Reliable data using implements of as UDP is an unreliable, the reliability is added to the transfer process, either by alternating bit or selective repeat protocol. Which is the what we learned down here with, I think this, the alternating bit. And then there is a selective repeat down here somewhere. Alright, let's go back.
Understand these RDT 3.0. So this is week 6 and we start with another new lecture, but we will be continuing with the same old chapter, which was chapter 4.
We're not there yet. I mean, I was, but...
Which is a protocol. In action. So we are going to understand both operations with no loss, although there are RDT 1.0, RDT 2.0, but we are going to understand RDT 3.0. What happens with the operation when there is no loss or when there is a lost packet. Now, in this protocol we are going to consider, we are going to take four scenarios when the sender is sending packets to the receiver, and there is no loss, there is a lost packet, there is a lost acknowledgement, or there is a delay in acknowledgement. So let's assume that
Alright, hold on. Let me do something real quick. Let me so my professor has these interactive problems here. Or not my professor, he gave us a link to these interactive problems. So let's do some of them. Internet, let's do these, and then I think we could do these. Alright, so the way I learned how to do this, hold on, let me, what's today, the 10th? No, I'll just email the professor later about it. So, what we need to do is, and I need to ask my professor, I hope he gives us the decimals, because then this will be easier. If not, I'm gonna be struggling. 95278. Alright, so now what we do is divide that by 2. I believe if we divide it by 2, we get a 1. So, 47. Uh, oh, you know what we could do? We could literally just do this. So, uh, 43303 divided by 2. Alright, so then we do, is it 21651? 10825. Yeah, so if it ends with a point 0.5, it equals 1. If it ends in a single whole number, integer, whatever, it ends with you put a 0. So 95278 divided by 2. And then divide by 2. Uh, yeah. So 23819 divided by 2. And you basically do this, 16 times, I believe. This, you get a 0 because it's even. What am I getting pinged for? Alright, what I gotta do here. This is for a 1488 divided by 2, 744, divided by 2, 372. Alright, hold on. Let me put a space there. Oh wait, no. Space there. So that's 4. That's 4. Divided by 2, 93. And then divide that by 2, so 46 is gonna equal 1. 23 equals 0. It's gonna be 11 equals 1. 5 equals 1. 2 equals 1. Then 2 divided by 2 is going to be 1, which equals 0. So now, what we do is this. 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 1, 0. And then we do 1's complement, so it's going to be this. And don't put any spaces in my answer. So if I put this here and then take the spaces out, this should be correct. Oh wait, this is the sum, so I think we do this first. How long am I studying for? Probably 8 hours. Because I got these videos that I had to go through, but I'm almost done with this. Because this, I found this person, they uploaded their lecture, and it's pretty much the same notes that I have, except gonna leave stream on for a while I do. Hey, that's what's up. Thank you. But they have like the same notes that I have, but I think they're on like version 6 of the book, and my notes are version 8. But they're pretty much similar. So I'm going through I've been watching these videos for the past 2 days, and gonna keep doing it till my exam on Wednesday. But because if I don't pass this exam, I don't pass the class. So I've been very trying to study it, but I'm so scared that I'm gonna get a question and I'm just gonna forget every fucking thing I know. They're gonna say, "What does TCP mean?" and I'm gonna fucking forget. Like I'm so scared of that because this one exam, this one professor, I feel like is gonna throw some
So in
wild
that case,
cards.
what will happen? Some of the data will
No.
be dropped or it will be corrupted, just like you have experienced congestion on the road. So for
Alright, let me see what this. I should, I would play like some like lo-fi music, but I have to watch these videos, so that's the thing. Alright, so if I don't know, is that a space right here? Networking, yeah. So if I hit check, incorrect. No, 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 no. That's some bullshit. Hold on. 0, 1, 1, 1, 1, 0, 1. Check. I took a class like this. It's very annoying. Yeah. Thing is, I don't. It's harder for me. Like, it's hard for me to study for this because I simply don't care. So it's 10. I feel like it's 10 times harder for me because for me to try and want to understand it, it's just like, bro, I got so many other things I could really be doing, but this class is so boring. I do not care. Did I add these numbers up wrong? Let me see. My calculator. And I hope if I get a question like this, I hope my professor gives us the decimals. I don't really feel like doing the whole conversion here. 43333519527 Yeah, but we divide that by 2. We got 0, 1. But then if I wait a second. Oh, no, no, 21,651. Yeah, it's 1, 1. How's this wrong? Unless I did some math wrong here. Hold on. Thing is, it sucks because something like my exam, I won't know if it's wrong. So this is so annoying because it's on my exam I only get one chance. I wish it wasn't like that when it comes to problems like this. Alright, that's a 0. We have 1, 1. Wait. Unless I'm supposed to go one up instead of doing 46. Let me see something real quick. $3.38. Alright, so based on this, 111,0,0,1,0, and then the trend would follow. Carry. The way that I learned how to do this versus what my notes are saying, the notes are complete. It's harder to figure out the notes. I don't get it. Skip it. Is this? Alright, let's see. What did I mess up here? I had the first part right. The first one is 1. Is that true? What? Uh, that's... They have it wrong. That's not right. Well, then this will be... That would be 0 then. But I'm gonna try another one because they definitely had that wrong. Alright, 63,900. Oh wait, it's not equal to 1, it equals 0. equals 1. This is gonna be 3 equals 1, right? Let's fucking go. I got it right this time. Alright, so it's gonna be 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1. I got them both right. Mephisto went live. What the fuck? That man hasn't been live in like 3 months, feels like. And he's streaming Unite. That's what's up, that's what's up. Alright, and then now we have another interactive problem. Which, this is the probably one of the harder ones. So let me see. T equals 0. I hope he doesn't have one of these problems on the exam, because this shit, I think it's wait for act 0. What is the receiver state? These are the receiver states. Wait from B, wait for, I think it'd be wait for 1 from, what? No, it would be 0? Yeah. Time T equals 0. What is the sequence act number? I think it'd be 0. T equals 1. B, wait for, what is the receiver state? Is there 0? I don't know if this image is in relation to the problem. Damn, $5,000 he needs? Escape Russia, leave safety from a war. Damn, that's a lot. Alright, what is the sender state for 3? How many times is the payload received at the highest layer? I think it's 1. Yep. Yep. Alright. This is another one. What is the missing transition? S0. send, I think. Looks like R0. No. Oh wait, no, we send it, so it should be R1. What? I don't know how. Let me try again, that don't make sense. S6. Reliable data transfer receive. Looks like it'd be S7. Wait, if it's S, then this is R3. No. It said S0. The R0? That doesn't make sense, because I guess I had to look at what goes after it, too. Because I gotta see if it has corrupt or not. S1. And corrupt and is ACK. It's looking like... Wait, S1. I think it's looking like S2. Yep. S0. Sends and then goes to S3, so it's not corrupt. I think it's R0 because send packet data checksum sequence number is 0, so it's gotta be R0. R0 S4. It's not corrupt. Then it goes to is ACK, so it's gotta be S3. I'm killing it, bro. Oh my god, I'm killing it. S0. Make packet, so it's not corrupt and has sequence number. It's gotta be R0. No? What? What's S1? Receive and corrupt or is ACK. Oh, then this would be R2. Bro, what the fuck? It says... Oh wait, or has sequence number. So then how are you supposed to know? So this has to be R1. R4? R3? What? Oh, wait for 0 from below. So S4. So it's wait for a call from one from above. It looks like it's gonna be... So wait, receive packet. Looks like it's gonna be S5. Yep. See, this is the thing. Oh my god. This is the annoying part because it's like... On the exam, if there's one of these and I get it wrong once, the whole thing is just, I don't get another chance. And it's like, what is the source port for packet C? 6243. Destination port 6850. This is UDP, right? Yeah. Source port for packet B 6850. For packet D 6850. That was easy. There's no point in that. Alright. Source. The source port is 6670. Trying to see what the hell the difference is for this one. Packet C. It's looking like 5703. Oh, I see the difference. This has a A and B, and this has separate. Okay. Alright. We did those interactive problems. Let's go back to the video.
Sender sends packet 0 to the receiver. It receives the packet 0 and it sends the acknowledgement 0. After receiving the acknowledgement, the sender will send packet 1 to receiver. It will send the acknowledgement 1 to the sender. After receiving the acknowledgement 1, it will send the packet 0. So actually it revolves like 0101. So packet 0, acknowledgement 0, packet 1, acknowledgement 1, packet 0, acknowledgement 0. Like this, the packets are sent from sender to the receiver using the transport layer. So this was an ideal situation when nothing is being lost or there is no error. Now let's assume that, for example, sender has sent a packet 0 to the receiver, receiver has received and it has sent the acknowledgement. Now sender has sent the packet 1, but this packet gets lost, right? Now how long should the sender wait, and how it will know that it has been lost? So now how long the sender has to wait to be certain that something has been lost? Sender will wait until as long as the round trip delay between the sender and receiver, or we call it as the time out, plus whatever amount of the time is needed to process a packet at the receiver. So it will receive for a certain amount of time which is required for sending the packet receiving the acknowledgement and processing the packet at the receiver time. So it will wait for some time until the timeout to to get the acknowledgement. Now, if the timeout period has passed and sender has not received the acknowledgement for the packet 1, it will assume that packet has been lost over here. So now sender will send the packet 1 again. So this was an example of the lost packet. So before sending a packet again, the sender has to wait for a certain amount of time, which is called as the timeout time, before the sender sends another duplicate packet again. So now the sender sends packet 1 again to the receiver, and receiver packet 1 is received by the receiver sends the acknowledgement, and then sender sends the packet 0, gets the acknowledgement. So sender has to wait for the time, for the round trip time, sending the data, acknowledgement, and plus processing time, in order to know that something has been lost, right? So this was the case of when packet is lost. Now what happens when acknowledgement is lost? So in this case, what will happen? For example,
See, my professor added this shit in here, but it seems like such irrelevant stuff.
let's assume that sender has sent the packet 0. It has received the acknowledgement 0. Now sender has sent the packet 1, and now within the timeout time, sender has not received the acknowledgement 1 from the receiver. Receiver has sent the acknowledgement, but that acknowledgement is lost. We know why it is lost, because we know that sometimes router is full, there is congestion in the network, so router may drop some of the packets. So let's assume that acknowledgement is lost. So during that timeout time, the receiver does not receive the acknowledgement. So what receiver will do? It will send the packet again to the sender. So this will contribute, or it introduces the possibility of the duplicate data packets at the receiver side. So now when the receiver detects the duplicate for the packet 1, it sends the acknowledgement 1 again. So after receiving the acknowledgement 1 for the packet 1, receiver sends the another packet.
That's basically this. What's it? Here, handling duplicates. Sender retransmits current packet. Thing is, we talk about NAC, but we never. I don't know why he. We never talk about NAC. Sender retransmit packet on receipt of NAC. But it doesn't. I don't get it.
It and receives the acknowledgement. Now from the sender's viewpoint.
Thing is, I don't really, I hate this because I don't need to understand it. I just need to memorize it. Unless he asks conceptual questions, if they're just questions based off the information, then I just need to memorize it. If he doesn't ask like in what real world scenario would this happen, then I don't need to completely understand it. That's so annoying.
Retransmission is you can say it's a nightmare. The sender does not know whether a data packet was lost and acknowledgement was lost, or if the packet or acknowledgement was simply delayed. So in all the cases, the action is the same, which is retransmission. So implementing a time-based retransmission mechanism, it requires the countdown timer, just like we are talking over here, the timeout. It requires a countdown timer that can interrupt the sender after a given amount of time has required. So in this case, the sender will not be will need to able to start the timer each time a packet is sent, and respond to the timer interrupt, and stop the timer. So these are the three things. Now let's talk about over here when the acknowledgement is delayed actually. So timeout is there, but acknowledgement is delayed. So let's assume that sender has sent a packet 0, received the acknowledgement 0 for the packet 0. Sender sends a packet 1, a receiver sends the acknowledgement 1, but it the acknowledgement is received after the timeout time. If you see over here, the acknowledgement is received after the time has out. It was not lost, but it was delayed now. So after the timeout time, the counter has expired. Sender has sent the packet 1 again. Now it will detect the duplicate packet, it will send the acknowledgement 1 again. So now there will be duplicate packet also and duplicate acknowledgement also. So this is what the retransmission is actually a panacea, or it is actually a nightmare at the sender side, because there can be it's nothing clear whether data packet is lost, acknowledgement is lost, data packet is delayed, or acknowledgement is delayed, right? So we have some pipelined protocols. So protocol which we discussed now, it was RDT 3.0. It's a functionally correct protocol, but it is unlikely that anyone would be
Pipelining, like, we just skipped all this shit here. Hold on. If packet or act is delayed, not lost, retransmission will be duplicate. Use countdown timer.
happy with its performance. So it is not, the performance is not well, especially in today's high speed networks. So the problem actually with this protocol is stop and wait. If you see, if you have carefully seen over here, the sender sends the packet, stops. When it receives the acknowledgement, only then it sends the another packet. So it is working like a stop and wait protocol. It sends the packet, stops and waits for the acknowledgement, then it sends the another packet again. So there is a performance problem with this type of stop and wait protocol, especially in today's high speed networks. So the solution to this problem is simple.
Pipelining allows multiple sender, range of sequences we increase. Buffering at sender receiver. Thing is, the buffering thing gets mentioned back in the next chapter, chapter 4, like at the end. Talk about the buffering and the tunneling.
Rather than to have stop and wait in this manner, sender can send multiple packets without waiting for the acknowledgement. And if sender is allowed to transmit 3 or 4 packets before having to wait for the acknowledgement, so the performance will be increased. Since many in-transit sender to receiver packets can be visualized, this technique is known as pipelining. So pipelining means we have like designed a window. Window has a size, for example 4 or 5. Sender can send 4 or 5 packets at a time. After all these 4 and 5 packets have been received by the receiver, and for all these 4 and 5 packets the acknowledgement has received, then the next packets will be sent. So this is called as pipelining. So sender allows multiple in-flight yet to be acknowledged packets, right? So 5 packets are sent, first packet is not yet acknowledged, so it has sent multiple packets. Range of sequence numbers must be increased when this type of pipelining approach is used. Sequence numbers should be increased. There should be a buffering at sender and receiver size, and range of the sequence number and buffering requirement depend on the manner in which the data transfer protocol responds to the loss. So if you see over here, stop and wait protocol, one packet is sent, the sender stops and waits for the acknowledgement. Then another packet will be sent, sender will be stopped and wait for the acknowledgement. Now for the pipeline protocol, if you see over here, there a certain size of window is defined. For example, sender can send 5 or 10 packets, right? It has sent maybe 10 packets. Now it will wait to get the acknowledgement for this 10 packets, then it may send 10 or 15 packets again. Now range of sequence number, can be increased. For example, it has sent first of all 5 packets, then it can send 7 packets or 8 packets.
Wait, what?
Now range of sequence number can be increased. For example, it has
I got an email. What? What page? Oh, it's this one. Oh wait, I could close this page.
send first of all 5 packets, then it can send 7 packets or 8 packets. There are two generic forms of the pipeline protocols, which are go back N and selective repeat. Now these are an example of the pipeline protocols. We are going to discuss these two protocols, which are go back N and selective repeat. Now what is it? Go back N and selective repeat. Go back N. Sender can send n unacknowledgement packets. So n can be any number, 5, 10, 15, 20, 100. So sender can have up to n unacknowledgement.
Yeah, this is where the notes get a bit messed up here.
Packets in the pipeline. Receiver only sends cumulative.
Thing is, I understand, not this image. This image. Well, I understand this. So it doesn't move up until it gets this, and then when this times out, it ignores the duplicate ones and then just resends 2, 3, 4, 5. Because it has to wait till it gets, I think, 3. Its max, and then it can move up when it gets the acknowledgement. And then, yeah.
Acknowledgement. So receiver will not send acknowledgement for one by one. For example, if it has 10 sent 10 packets, it will not send 10 acknowledgement. Rather, it will send acknowledgement and it will number it as 1 to 10. So cumulative acknowledgement are sent. But it will not acknowledge the packet if there is a gap. Sender has a timer for the oldest.
This thing's important. Cumulative. This is used somewhere else also. Try. Axe all packets up to, including sequence. Thing is, we did a quiz in class, but he doesn't. I'm gonna ask him. Probably not. I don't know. We did a quiz, and I don't know. He didn't. He doesn't open up the quiz, and I'm just like, damn. I want to see if those type of questions what I got wrong. But nope. Let me just double check. Oh wait, no, he did. What about the last one? Oh no, he opened it up. Okay, let me see what I got wrong.
So hello everyone,
No.
this is week 5 and we start with another new chapter in this week, which is chapter 4, and in this chapter we are going to cover the third layer, the third layer from the top of the
Alright. What did I get wrong? 32 bits. Total number of hosts. How the hell did I get this? I'm trying to think. Yeah, oh man. I know this now. I know this now. IP diagram has at least 20 bytes. I'm trying to see if maybe this would be part of the exam, hopefully. Repeats questions. Oh, you know, I could do is check the first. No, he hid the questions on the first exam, so you can't see it. But I wonder. Let me look at the first quiz. Nope. First quiz, you can't see anything on. Alright. Let's see what I got on the second quiz here. Again, 8 out of 10. Transport layers. Segments, yep. Internet transport protocol. Which one of the following transport layer protocol used in internet? TCP, yep. The receiver includes the RNW and the RWND5. Free buffer space at the receiver end. And this is supposed to be chapter 3. I think there's a chapter 4 type notes. Cause I know definitely at the end of this. Oh, and I don't know if I need to know about all this extra stuff here, because she doesn't go over open flow. So, thing is, if I don't learn it, it's gonna be on the exam. So that's so annoying. Alright, let me see. Where was this at? Hmm. I don't know. Free buffer space at the receiver. I need to remember that. The operating system uses. Yeah, the destination port. With the SR protocol. Oh, because I didn't know what SR meant. It's selective repeat protocol. It is possible for the sender to receive an ACK for a packet that falls outside of the current window. Apparently that's true. I don't. Usable, not sent, not usable. Out of order. Buffer. Wait, for the sender to receive, let me see. Hmm. 3 duplicate acknowledgements. It will go ahead and retransmit the packet right away, even before a timeout. Fast retransmit. Used to check for errors in the transmitted segments. Yep. See, like, if the exam is literally like questions like this, easy A, I believe I can get. But because there's free response questions, I'm scared for my life. Because the free response questions is literally where I I think I'll blank. Because I'm not good with words. Do do do. Alright, let's go back. Close these.
Acknowledged packet, and if the timer expires, it will retransmit all the unacknowledged packets. Alright, so let's understand this. First of all, we will understand go back n, then I will explain the selective repeat. So for example, there are k bits sequence number in the packet header, and there is a window of up to n consecutive unacknowledgement packets which can be allowed. So if you see, different colors are used. White means this is not yet usable. Blue means it is usable, not yet sent. Yellow means it is sent, not yet acknowledged, and green means already acknowledged. So acknowledged, all the packets up to, it can include up to some sequence number. So cumulative acknowledgements can be received, and it can receive duplicate acknowledgement. There is a timer for each in-flight packet, and timeout retransmit the packet n and all higher sequence packets in the window. Alright, so go back n, let's understand over here. Go back n. Alright, so in this figure, if you see over here, sender sends packet 0. For example, let's assume that there is a buffer size of 3 packets to send. So it sends packet 0, packet 1, packet 2 and packet 3, 4 packets at a time. So it has sent 4 packets at a time. Packet 0, packet 1, packet 2 and packet 3. Now it waits because the buffer is full. Now packet 2 is in between lost. So after receiver receives packet 0, it sends the acknowledgement 0. Now when it receives the acknowledgement 0, it sends packet 4. So if you see, packet 0 was sent, packet 1 was sent, packet 2 was sent, packet 3 was sent. So when packet 0 is received, acknowledgement is received, that means it becomes the usable space. So the sender sends the packet 4. Now acknowledgement 1 is also received, this becomes the usable space, so it sends the packet 5 over here. The sender sends the packet 5. But in between, packet 2 is lost. But sender, after sending the acknowledgement 2, receiver does not receive the packet 2, but it receives the packet 3. This packet is lost. So what happens at the receiver side? Since the packet 2 is not received, receiver receives packet 3, it will discard the packet 3. It sends acknowledgement again and again. So it sends acknowledgement 1 again.
What I'm going to do is I'm going to finish up chapter 3, and then later tonight I'm going to do chapter 4, because I need a break in between. I can't do this straight, because if I study something straight, it's too much. I need a break in between.
So in between, receiver also sends packet 4 and packet 5 because the acknowledgement for the packet 0 and packet 1 has received. Now when packet 2 out, the time out for the packet 2 is received, and the acknowledgement for that packet is not received. So the sender will send packet 2, packet 3, packet 4 and packet 5 again. Why? Because go back n means the packet which is lost, after that whatever the packets it sent, it will send again, although maybe those packets have already been received by the receiver. If you see over here, packet 3 is received but it discards. Packet 4 is received, it discards. Packet 5 is received by the receiver, it discards. Why it discards? Because packet 2 is not received by the receiver. So if you see over here, now at the sender side, packet 2 it sends again, packet 3 sends again, packet 4 sends again and packet 5 sends again. So it delivers and sends the acknowledgement 2 and acknowledgement 3. So if you see over here, The packet that is lost, after that all the sequence number of the packets that were sent by the sender are sent again. So this is called as go back N. So go back and send all the N packets which were sent after the lost packet. So it actually contributes to the duplicate packets at the receiver side. Selective repeat. Selective repeat is quite better than go back N. Again, the sender can have N unacknowledgement packets. Receiver acknowledge individual packets. Sender will maintain as usual the timer for each of the packet, and when timer expires, it transmits only the unacknowledged packets. So, but here the time it transmits all the unacknowledgement packets. So this is the difference. So selective repeat is quite better than the go back N. So in case of selective repeat, receiver individually acknowledges all correctly received packets and it buffers the packets if the packets are received out of order. Sender will only resend the packet for which acknowledgement is not received. It will not send the packet, it will not send all the packet. Sender window, as usual, it has consecutive and sequence numbers. Again, it limits the sequence numbers of the sent and the unacknowledgement packets. So let's assume over here we have the same thing. White stands for sender view of the sequence number and receiver view. Not usable. It is usable but not yet sent. It's in the buffer yet. It's yellow means it is sent and acknowledged, not acknowledged. Green means sent and acknowledged. Now here in case of receiver, what we have, gray means it is expected but it is not received. Pink means it is out of order, and blue means it is acceptable. Alright, so selective repeat. If the next...
Oh my god, bro, there's 94 slides. This is why I hate this class. So much information.
Available sequence number is in the window, it will send the packet, and it will resend the packet for a particular number N, and it will restart the timer for that resent packet. For acknowledgement, it will mark the packet N as received, and if N is the smallest unacknowledgement packet, it will move the window, it will advance its window. Then at the receiver side, what happens? It sends the acknowledgement number N for the nth packet received. Packets received can be out of order. If it is out of order, it will buffer those packets. If the packets received are in order, it will deliver. Also, it will advance window to receive the next packet, and it will mark it as expected to receive but not yet received. Packet N will have acknowledgement number, otherwise it will ignore. Alright, so let's check this example over here. So let's understand, because both the sender and the receiver side, they contain the buffer. Let's assume that the buffer size is of the 4 packets. So these 4 packets are marked for sending 0, 1, 2 and 3. So at the receiver side, packet 0 is received. Now it advances its windows and 1, 2 and 3, 4 are marked as they are expected to be received but not received. So when packet 0 is received, it sends the acknowledgement 0. Now at this point, packet 1 is also received, acknowledgement 1 is sent. Packet 2 is lost. So packet 2 is lost. Now packet 3 is also sent, and it is received by the receiver, but it is buffered because packet 2 is
What are these people doing out there?
not received, but packet 0 is received, it sends the acknowledgement 0. Now at this point, packet 1 is also received, acknowledgement 1 is sent. Packet 2 is lost. So packet 2 is lost. Now packet 3 is also sent, and it is received by the receiver, but it is buffered because packet 2 is not received, packet 3 is received. So at this point, it will not discard it, rather it will be buffered and it will send acknowledgement 3. If you see, acknowledgement 0, acknowledgement 1 is sent, but acknowledgement 2 is not sent, acknowledgement 3 is sent. Now, since it has received the acknowledgement for 2 packets, so it advances the window. When acknowledgement 0 is received, it advances the window and sends the packet 4. When acknowledgement 1 is received, it advances, sender side advances the window and packet 5 is sent. So packet 4 is received by the receiver, it is buffered, acknowledgement 4 is sent, packet 5 is received by the receiver, buffered, and acknowledgement is sent. Now packet 2, after the timeout for timer has expired for the packet 2, packet 2 will be resent again. So when the timer has expired and sender sees that acknowledgement for the packet 2 has not received, so it resends the packet again. So packet 2 is now received. Now whatever the buffered packets were there at the receiver side, it marks them as delivered. So packet 2 is received, packet 3, packet 4, packet 5, they are marked as delivered, and at this time acknowledgement 2 is sent. So when acknowledgement 2 is sent, acknowledgement 3, acknowledgement 4, so it will increase the buffer size of the window and advance to the next packet. So if you see over here, in selective repeat, only the packet for which acknowledgement was not received, that packet is resent. Whereas in go back n, if a particular packet is not received, not only that packet, but after that, whatever the number of packets were sent, all of them will be resent again. So this actually contributes to sending of the duplicate packet, and this is the difference between the go back n and the selective repeat.
That doesn't match anything with what that quiz said. Let me go back to it. That doesn't match. Was it quiz? No, I think it was quiz 2. Doesn't match that at all. With the selective repeat protocol, it is possible for the sender to receive an ACK for a packet that falls outside of its current window. Based on what, how is this true? This makes complete no, like this doesn't make sense at all based on how this is set up. Because it only moves the window for the sender to receive. If next available sequence and number in window. That just doesn't, I'm gonna have to ask him about that, because that doesn't completely make sense based on the way this is set up. That should never happen.
Protocols of the transport layer. Alright, so next topic.
Alright, well we finished this video, but hold on. Sender after window, after receipt. Will accept packet with sequence 0. Okay, so that makes sense here. Will accept packet with sequence number 0. Oh, because the receiver... That still doesn't make sense, because I understand if this meant the receiver to receive a packet that falls outside of its current window. Because if it's saying packet 0, then yes, this will accept the sequence number packet 0 right here, despite it actually not being. This doesn't make sense. Alright, the next video, I believe this is still chapter 3. Yep. Ah man, 2 hours for one video. That's alright.
So hello everyone, we continue with our chapter 3 in this lecture. We already started with chapter 3, which is the transport layer, in the last lecture, and we completed many of the concepts related to the transport layer. In this lecture, we are going to continue with the remaining concepts of the transport layer, which is connection oriented transport, which is TCP. Then we are going to talk about principles of congestion control, and then we are going to talk about TCP congestion control. How does the TCP handles the congestion control? Alright, so let's start with this. We have already talked about in detail regarding the TCP transmission control protocol, which is an important protocol of the transport layer. It's a connection oriented protocol. Connection oriented means before sending data to the receiver, TCP makes a handshake or makes a connection with the receiver, a logical connection. So the connection is followed in the 3 steps. First of all, connection is established, then data is transferred, and then connection is terminated. So just quickly, let's have an overview of the TCP, the characteristics of the TCP. First thing is it's point to point. There is a point to point connection establishment. So one sender, one receiver, just like the circuit switching. We talked about circuit switching also in chapter 1. It is also point to point, one sender and one receiver. Similarly, TCP is also point to point, one sender and one receiver. It is reliable in order byte stream. So it's a reliable protocol, and it transmits the bytes or the data in order. So the data, how it is sent, it will be received in the same order at the receiver. There are no message boundaries. It's a pipeline. TCP congestion and flow control, it sets the window size. We learned about the 2 protocols, the pipeline protocol. How does the TCP sends the segments? Like it defines a window, and in the window it puts like 3 or 4 frames. So as and when the frames are delivered, it keeps on adding the segments in the pipeline. So there are send and receive buffers at both the sides. So we have at the sender side there is a TCP send buffer. Buffer is nothing but a temporary memory location, and at the receiver side we have a TCP receiver buffer. So the TCP segment buffer, before sending, the segment is first of all saved in the TCP send buffer area. Then from the buffer area it is transmitted on the transmission medium. At the receiver side, the segment is first of all received in the buffer area, and after that it is sent to the application layer. Next is TCP is full duplex data. That means there is a bidirectional flow in the same direction. Full duplex means at the same time both sender and receiver can send. So actually we have the communication can be either simplex, half duplex or full duplex. Simplex means only one side can always send, just like in the client and server. Server can always send, right? So, or we can say the master computer can always send. So simplex means the data always flows from one end only. Just like in your computers, data always flows from keyboard to the monitor. Never ever the data flows from monitor to the computer. So that's an example of the simplex communication. Half duplex means both parties, both sender and receiver can send the data, but at a particular time only one person. So for example, in half duplex, if the sender is sending the data, receiver cannot send. If the receiver is sending the data, sender cannot send. Example of half duplex is the walkie-talkies. You might have seen the walkie-talkie in the hand of the policemen or the security personnel which are standing on the airports, or the security guards. Last one is the full duplex. Full duplex is, you can say, quite more advanced form of communication. Full duplex means both sender and receiver can send data to each other and at the same time. So it's a bidirectional data flow. In half duplex also it's a bidirectional data flow, but only one can send at a particular time. So it's a bidirectional data flow in the same connection. So in the same connection, both sender and receiver can transmit at the same time. And it defines the maximum segment size. Maximum segment size means what is the maximum number of bytes that a segment can carry. Next is, it's a connection oriented. That means there is a handshaking, exchange of control messages between the sender and the receiver before the data is exchanged, just like the circuit switching. It's a flow control. TCP has a flow control. That means sender will not bombard the receiver with a lot number of segments. That means sender will not overwhelm the receiver. It will send the segments at a particular flow which a receiver can handle. So this is all the characteristics of the TCP. Moving ahead. This is a TCP segment structure, very important to understand the segment structure. You will see this type of segment structure when we start with the Wireshark, maybe in week 5 in our lab. So we are going to talk about all these segment structures in the lab also. Okay, so the TCP segment structure, this is a TCP segment structure. These are the fields in the segment structure. The size of the TCP segment structure is 32 bits. Sorry, it's not 32 bits. Yeah, it's 32 bits. No. The size of the TCP header is actually 20 bytes. Source port and destination port, they are 32 bits. So the size is different. Let's talk about TCP header is 20 bytes. But whereas UDP header is, I think it's 8 bytes.
Yeah, it's
UDP header is 8 bytes and TCP header is 20 bytes. This is TCP header or the segment structure. This is 20 bytes. So let's talk about the TCP segment. It is almost some fields are similar to the some fields are similar to the UDP segment or UDP datagram. Okay, so let's talk about this one, source port and destination port. Source port and destination port number are used to specify the port number of the source application and the destination port number of the source application. Next we talk about sequence number. Sequence number is 32 bits, that means 4 bytes, and acknowledgement number is also 32 bits. These are used by TCP sender and receiver for sending the reliable data transfer service.
Wait.
After this,
is source port in all 16 bit? Oh, it is 16 bits. I'm so stupid.
Is also 32. So
let me just see.
Okay, so let's talk about
I think they're both 16, right?
Source port and destination port. Source port and destination port number are used to specify the port number of the source application and the destination port number of the source application. Next we talk about
I think they gotta be 16, right? Because of the checksum. There's 4, 8. So there's 16 bytes. The sender, receiver, checksum. You add the
sequence number. Sequence number is 32 bits. That means 4 bytes. And acknowledgement number is also 32 bits. These are used by TCP sender and receiver for sending the reliable data transfer service. After this, we have a receive window. Receive window is 16 bits, that means 2 bytes. This is used for flow control, and this is used to indicate the number of bytes that receiver can accept from the sender. Then we have the header field over here, header length field. This is a 4 bit, sorry, not even a byte, it's 4 bit. It specifies the length of the TCP header in 32-bit words. TCP header, it can be of variable length. It can be of variable length because of the TCP options field, because options, this is of variable length. It can have any size. Then we have over here options field also. This one, options field. Options field is of variable length, and it is used when a sender and receiver negotiate for the maximum segment size or for a size of the window or the window scaling factor. Now if you see, this part is not used. Then we have, if you see, UAP, RSF, these are the flags, 1 bit each. So there are 6 flags. So this is 1.
6 flags. I got more than 6 flags though here. Oh, because we aren't using 2 of them. U and I don't know what U and P are, but
1 bit each, and total they carry 6 bits. So the flag field contains 6 bits. Now we have, A stands for acknowledgement flag. It is used to indicate that the value is carried in the acknowledgement field is valid. Then we have R, reset, SYN and FIN. So this one, R, S and F. Reset, SYN and FIN. These flags are used for the connection establishment in the beginning and for the connection termination at the end. Then we have this P flag. It stands for push. It indicates that receiver should pass the data to the upper layer immediately. And finally we have this U. U stands for urgent. Urgent bit is used to indicate that there is data in this segment that the sending side upper layer entry has marked it as urgent. And next we have the urgent data pointer. If you see over here, urgent data pointer, the location of the last byte of this urgent is indicated in the 16-bit urgent data pointer, and TCP informs the receiving side of the upper layer when there is some urgent data, and it needs to pass it a pointer to the end of the urgent data. Checksum is used to calculate the errors. If there are errors in the data when it is received, so this field is used to check the errors. It performs some calculations on the received data. Push data, P is not mostly, it is not used. Urgent data is also generally it is not used. This is receive window specifies how many bytes receiver is willing to accept. So this actually controls the flow control. So this is actually related to the flow control, so that the receiver is not overwhelmed if the by the sender by sending too many segments at a particular time. The last one contains application data. Application data is the user message, and it can have the variable length. Alright, now in this we talked about sequence number and acknowledgement number. It's very important. When the TCP sends the segments, it puts number on the segments so as the segments can be differentiated from each other. So these are two important fields, sequence number and the acknowledgement number, and these are the critical part of the TCP's reliable data transfer service. So sequence number, what is a sequence number? It's a byte stream number of the first byte in the segment's data. So every segment is always numbered by the TCP. So sequence number is just a number on the of the first byte in the segment data, and it is chosen as a random number. Okay, so now what is acknowledgement number? It is the sequence number of the next byte expected from the other side. It can be the cumulative acknowledgement also. Alright, now let's check over here. We have host A and host B. The first host A, let's say it types letter C in the segment and sends it to the host B, puts the sequence number 42 as a random number chosen for the first byte in the segment data. Acknowledgement number is 79 and data is C. Now after host B receives this data, it has to send the acknowledgement. Now in the acknowledgement number, the sequence number will be whatever the first segment that sender has sent to the receiver. So this acknowledgement number will become the sequence number in this acknowledgement segment. Now this is the acknowledgement segment. Now here, if you see over here, acknowledgement number is 43, but here the sequence number for 42. Now what does acknowledgement number specifies here? The acknowledgement number specifies here the next expected sequence of the segment which the source must send to the receiver. So this means that the next segment that host A will send to host B, it should carry the sequence number 43. This is what is the purpose of the acknowledgement number. So acknowledgement number specifies the sequence number, the expected sequence number of the next byte which the sender will send to the receiver. Now host A receives the acknowledgement and then it sends the final segment for connection establishment or whatever. So if you see over here, the sequence number is 43. Whatever the acknowledgement number was here, sequence number is 43, and here the acknowledgement number is incremented by 1. So this is how the connection establishment takes place, and this is how the exchange of messages takes place. The first sequence number is just a random number chosen by the host, and even the acknowledgement number. After that, it should be in the increasing order. If you see the acknowledgement number, the first acknowledgement sent by the receiver is the increment of the first sequence number, and the second acknowledgement number sent by the sender is the increment of the first acknowledgement sent by the sender. Now if there are out of order segments received by the receiver, so for example, sender has sent 4 segments. So receiver first of all receives segment number 2, then it receives segment number 3, then it receives segment number 1, and then it receives segment number 4. So these segments have arrived out of order at the receiver. So how does the receiver handles these out of order segments? So TCP does not specifies anything for handling the out of order segments. This is up to the software developer or up to the implementer how to handle these out of order segments if TCP protocol is used. Alright, now TCP, RTT and timeout time. We discussed about RTT in the previous lecture and timeout time, because each packet has a certain time specified, maybe 150 milliseconds or 100 milliseconds something. So in that timeout period, segment is sent and acknowledgement must be received by the sender. So that is called as time during that time lapse. So if during that time lapse acknowledgement is not received, that means sender will assume either the packet is lost or the acknowledgement is lost. Now the question is how to set the TCP timeout value, how the timeout value is sent. It should be longer than the round trip time, right? We understood the round trip time also. It should be, timeout value should be a little larger than the round trip time, but round trip time varies for each segment. If the segment is large, round trip time may vary for it. So timeout time should be larger than RTT round trip time, but how much larger? Should it be too large or how much larger? Now, if it is too short, then RTT, then there will be a premature time and there will be unnecessary transmission. So for example, if RTT round trip time is maybe 100 milliseconds, alright, so and if we give time out time as 80 milliseconds, in 80 milliseconds the segment may not be received or acknowledgements may not be received. So there will be unnecessary retransmissions, there will be unnecessary duplications occupying the buffer. But if it is too,
I completely forgot.
if it is too short for each segment, if the segment is large, round out value, how the timeout value is sent, it should be longer than the round trip time, right? We understood the round trip time also. It should be, timeout value should be a little larger than the round trip time, but round trip time varies for each segment. If the segment is large, round trip time may vary for it. So timeout time should be larger than RTT round trip time, but how much larger?
Oh my god, another 32 minutes. I'm trying to get through this. Oh my god. This shit is so. Oh my god, so much information I'm trying to take in. Round trip time. This is the one, like, the end of these chapters is where my weakness, I think, is. Because the end of the chapters is like where I'm just like, I'm so bored. Alright, let me think. Hold on, let me get up and stretch. Let me take like a 5 minute break and just say some talk. I don't know who's here, but you know, I'll just be talking for a bit. But I will be probably not be streaming after next weekend for like a month because I got finals, and then I got to drive my car back home to have it shipped. Um, I gotta start packing. I think I'm gonna start. I had to clean up my room a bit, so I'm gonna start packing this week. My monitor and desk not to being taken apart until like the 2 days prior to when I need to drive my car back. But yeah, I'm gonna need to start packing some of my stuff. I need to move my car back over here. Probably do that next weekend. There's a parking spot. And yeah, most of the stuff though, I don't even like what I'm taking to what I'm taking to California is I'm shipping my car and then I'm looking over here because my chat is over here. I don't know, but I'm shipping my car on the first week of May at some point, whenever they. I have it scheduled for Monday on the first week of May, so May 2nd or something. But they have a 1 to 5 open period, so they could literally come that Friday. But I'll be taking exams, so I won't be there. Uh, really, the first week of May is going to be another one of my busiest weeks I've ever had. So that's going to be annoying. Because I have, oh my god, I have my computer networks final and for I don't like the way they do final exams at school. I really wish it's more like I hate that it's all in 1 week. I wish it's spread out between 2 weeks instead of 1 week because that's just so annoying. Like I got one exam on Monday, which is for computer architecture. I don't think I got an exam on Tuesday, which thank God I need. Which is good because I don't have classes that day and I'm probably gonna be taking work off for that day. Um, for like literally, I think Monday, Tuesday, Wednesday, I'm taking work off for that week to focus on exams. And then not Tuesday, Wednesday, I got two exams. I got AI and Python. The Python one, I'm not too worried about because I kind of just have to look over my notes and I should be good. And then it's also going to be pretty simple because it's Python. But I don't know, there's still a month of school left basically, or 20 days left, whatever. So there's still information that we're probably going to be learning. Architecture is or not architecture, AI, artificial intelligence class. I've been doing good in that class. I have like an 86, but uh, I don't. Let me hold on. Let me look at the grading scale for his class. What is this? Wait, this is no. Am I thinking about architecture? I'm talking about the artificial intelligence class. Architecture class, I've been doing really good on those exams somehow. I don't know how, but no. What am I thinking? I'm thinking of the AI class is mostly multiple choice and stuff, but I have like the 86 in this class. If I get 100 on this thing, that's an 87. But if I get like a 75, that puts me at an 84, which I am fine with. But the final is 20%, or the next test is 20%. So, but I've been averaging his homeworks. I've not really been doing good on, but that's whatever. But I've been averaging good on his test B's, so I need to do some calculator test things for that. And then for my how class is this? My my computer architecture and organization class. I have a 94 in, and I somehow had a 93 on his last exam. And each exam was 10%, so that's good. But the final exam's 30% collectively. So let me see what my average for the midterms was 91%, which is good. But then the final exam, I'm so glad they don't do final exams as a collective uh, anymore. I think a lot of professors are told not to do that anymore because it's very stressful when it's over everything of the semester. That's uh that's some bullshit, really. Especially when you got three other exams the week of or four. So it's kind of like, bruh. But 30% though, I'm still in passing range for if I got a zero on it. But I don't think I'll get a zero on it. Because 94, if I got a zero, put me at 64. But I'm not gonna get a zero on it. But a lot of his exams are a bit. I think this next one's gonna be a bit weird, but that one I definitely am. It's on Monday, so I will be given a good opportunity for that Saturday and Sunday to study, and it's Monday morning. All my exams are in the morning, except my Python one. But it's gonna be stressful because Sunday my mom's supposed to drive me back to school, but I don't know what time. Which is kind of frustrating. Friday night I'll be driving back home, so that Saturday I'll be trying to study, but at the same time I think that whole week of the 25th and 29th, I'm going to be studying for the architecture one because that's the first one. And then because I'll be back at school, I'll have the Monday and Tuesday to study for the Python and AI, artificial intelligence one. Python one I also started to study that week prior, but the AI one, because it's mostly memorization, I'm just gonna be studying on that Monday and Tuesday because it's just if I as long as I memorize the stuff, I should be good. And then Wednesday and what was it? Monday, Tuesday, and Wednesday, I'll primarily be studying also for the computer networks one because that one I think is 2 chapters also, but I need to find out. Because if I get a good grade on this computer networks class exam and then a good grade on the next one, I could get a B in the class, but I'm just looking for a passing grade at this point, depending on what I get on this next exam here. So I could sort of have things planned out, but then once exams end, it's gonna be so busy, and bro, until I get to California and sit down and have everything set up for the summer, I will be so much less stressed than I am right now. And I'm not even stressed right now. I am, but you should see me the for my next exams or for the finals. I'm gonna be hella stressed, bro. 'Cause I don't know, but I will see. All right, let me finish this chapter up. Was this 32 more minutes? I'm gonna try and do it. Uh, and then tonight we'll go through half of the chapter 4, and then tomorrow night I'll stream the other half because there's too much information. I can't do it all in one day. It's too much.
Should it be too large or how much larger
Alright, let's go back because I have no
than the
idea where we're
is
at.
lost? Now the question is how to set the TCP timeout value. How the timeout value is sent. It should be longer than the round trip time. Right? We understood the round trip time also. It should be timeout value.
Wait a second, I just realized something. Hold on. When I have in our CRLF, what does that stand for? In our AI class, we have something. Control character. Okay, carriage return. Okay. In our carriage return, what does it say? Line feed. Okay. In our AI class, we used something at the end of their print out statement in Clips called CRLF, and I was like, wait a second.
You should be a little larger than the round trip time, but round trip time varies for each segment. If the segment is large, round trip time may vary for it. So timeout time should be larger than RTT round trip time, but how much larger? Should it be too large or how much larger? Now if it is too short than RTT, then there will be a premature time and there will be unnecessary transmission. So for example, if RTT round trip time is maybe 100 milliseconds, alright, so and if we give timeout time as 80 milliseconds, in 80 milliseconds the segment may not be received or acknowledgements may not be received. So there will be unnecessary retransmissions, there will be unnecessary duplications occupying the buffer. But if it is too long, then there will be slow reaction to the segment loss. Either the receiver has to wait for a longer time or the sender has to wait for a longer time to react that a particular packet is not received or a particular acknowledgement is not received. So it should not be too longer than RTT or it should not be too shorter than RTT. So how to estimate the RTT? Now the question is, we have a sample RTT. Sample RTT is measured, it's a time which is measured from the segment transmission until acknowledgement is received. So a sample RTT, when the first segment is sent, a sample RTT is measured. So when the segment is sent and after how much duration the acknowledgement is received. So this forms the sample RTT. It is this time is measured, segment transmission until the acknowledgement received. So retransmission, we are not going to count any retransmission time. For example, if this segment is...
How's the studying going? Just finished one assignment, got 3 left. God damn. It's a long ass assignment. You got a lot of it. I'm almost done with this chapter. I got 30 painful minutes to get through. Give or take, I pause it and look at things. But I'm gonna finish this chapter 3, and then later tonight, because I need to take a break in between. So later tonight, then I'll stream chapter 4, or first half of chapter 4 tomorrow. Finish it. I don't know, because my exam's on Wednesday. So, but the my weak points on these two chapters are literally the end of the chapters, because I get so bored towards the end. I'm just like, oh my god, I don't care anymore. So, but it's going good. I'm just afraid he's gonna ask one question, I'm gonna fucking lose everything. He's gonna ask like something about how to estimate RTT, like this right here, and I'm just gonna forget, and then forget that. I'll forget everything. So I don't know. Because the way his free response questions, he does a lot of those, and so the free response questions are like a lot of points, and so that's what I'll probably be doing first. So, but I don't know. He locked exam 1, so I can't see what type of questions he asked. I forgot. I was able to see it one time, but I didn't think if he'd lock it again. But I don't know if he asks a lot of conceptual questions, like if I just need to know the information versus if I need to know how to apply it. In which some scenarios I can, some scenarios it depends on what he's asking. But yeah. I'm glad though that most of my classes are just exams now, like for this month, and not many assignments, because it gives me a lot of time now to start studying. Like after this exam, I or after this upcoming week, it's really just finals. I don't have any other assignments really. And so I'm kind of glad because I'm going to start studying for those next. So I just need this semester to end. I'm so tired.
Lost, we need to send it again, or this acknowledgement is lost, we need to receive it again. We are not going to count any retransmission time. Sample RTT will vary, and we want another estimated RTT. So estimated RTT is the average round trip time of the several recent measures. It is not just current sample RTT. Sample RTT is actually the round trip time for maybe one or two segments, but average RTT or the estimated RTT is the round trip time which we average for several recent measurements. For example, it can be for the first 10 segments, or can be for the first 15 segments or something like that. Because the sample RTT time will fluctuate from segment to segment, because of the congestion in routers and varying load on the end systems, and because of these fluctuations, any given sample round trip time may not be of any use, or it may be a...
See, like this stuff, she just explains in this video about this, but my professor adds these in the notes, and I'm just like, do I need to know these? Like, I don't, this is like a lot of extra shit that I don't think I need to know, but you know. Last time I said that for an exam, when I was studying, I'm like, yeah, I don't know if I need to know these, and I took the exam, they were on there. I was like, damn. But I still got 81 or no, 85 on the exam or whatever. But this is just so much extra like stuff that I'm just like, why?
Typical. So in order to
I meet with my professor on Tuesday, so I can ask him a lot of these questions.
estimate a typical round trip time, and in order to be more calculative, uh, we that's why takes sort of a average of sample RTT values. So TCP maintains an average called estimate RTT of the sample RTT values, and after obtaining a new sample RTT, TCP updates the estimated RTT by using the formula. We are not going to discuss the formulas and not going to discuss
Yeah, she said we don't not gonna discuss the formulas, so I don't know. I
much in detail. Alright, so that
see. I want to believe her, but my professor probably gonna be like, all right, what's the formula? I'm gonna be like, I don't know.
was the segment structure. Now we talk about the reliable data transfer. How does the TCP handles the reliable data transfer? Although these are given much in detail, this one segment structure, but we are not going to talk much about it. We discussed that TCP creates RDT, reliable data transfer service, on the
This is why I'm confused. I could have sworn we already talked about this shit. It goes out of order. Something happens here.
TCP creates IP and is a cumulative reliable data
I don't know where
TCP sender
these notes came from.
of transport layer.
Yeah, so she just... Okay. She just went back.
We have the application layer. Data is received from the application layer. After receiving the message or the data, TCP creates a segment. When TCP is used, we call it as a segment. When UDP is used, we call it as a user datagram. So a segment is created with the sequence number. Sequence number is nothing, it's a byte stream number of the first byte in the segment. It starts the timer if it is not already running, and it waits. There is also an timeout interval which is called as the expiration interval. So if during that timeout period, within that time frame, the acknowledgement is not received from the receiver, it will retransmit the segment because it caused the timeout, and it will restart the timer again. Sender will restart the timer again. Now acknowledgement, if after the acknowledgement is received, if acknowledges previously unacknowledged segment, so if the receiver has acknowledged the previously sent but unacknowledged segments, sender will update what is known to be acknowledged. So sender will update that, for example, sender has sent 4 segments, right? So receiver has acknowledged first 3 segments. So it will update that first 3 have been acknowledged and the last one is yet to be acknowledged, the 4 segment. It will start the timer if there are outstanding segments. Now let's talk about the flow control.
Is this or... I understand retransmission. I don't know why there's nothing on this slide, so I don't know what it's supposed to do. Yeah, I understand this. Sequence 92, 8 bytes, 20. This sends 100, this sends 120. But okay, so is this like early timeout or something? It looks like it. So it looks like it resends it, but since cumulative act, this is where this word comes in again, cumulative act.
So,
And then what is this? I get that 100, 120. So the sequence is 120. I don't know where this 15. Is this just covers for earlier? Oh, because is it because of this? Alright. Cumulative act covers for earlier lost act. Oh, because it doesn't know it got lost, so that's how it was able to send for 120. Okay, okay. Oh, wait. And yeah, she doesn't even go over fast retransmit. If sender receives 3 additional acts of the same data, resend unact segment with a small sequence. Alright. See 3 duplicate acts indicates 3 segments received. That's a duplicate. Is it because it's do 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 do. Alright. So next, okay, so fast retransmit, resend with the smallest sequence number. Resend unact, okay, yeah, unact.
flow control to handle the flow control so that the TCP does not overwhelm
Was this 33 more minutes?
the receiver.
I know, it's 23 more minutes.
There are sender and receiver buffers. So we have a TCP data in buffer and a spare room. So receiving side of a TCP connection has a receive buffer. This is, for example, a receive window. This hole is for the receiver buffer. Half of it is occupying data and half of it has a spare room to put the more incoming data. Application processes, why we have a buffer? Because application processes may be slow at reading from the buffer. That's why everything is first of all stored in the buffer of the receiver, and then one by one it is delivered to the application layer.
My brain just did not comprehend any of this. Hold on.
Flow control, to handle the flow control so that the TCP does not overwhelms the receiver, there are sender and
I feel like there's an image in here of this. It's right here.
receiver buffer. So we have a TCP data in buffer and a spare room. So receiving side of a TCP connection has a receive buffer. This is for example a received window. This hole is for the receiver buffer. Half of it is occupying data and half of it as a spare room to put the more incoming data. Application processes, why we have a buffer? Because application processes may be slow at reading from the buffer. That's why everything is first of all stored in the buffer of the receiver, and then one by one it is delivered to the application layer. So flow control is basically sender will not overflow the receiver's buffer by
I feel like the images my professor put in the notes are not good compared, like this image does a lot more of me understanding. Because this makes sense. These image, I don't know what the hell this image very means.
transmitting too much or too fast. So for example, receiver
This,
buffer
yeah,
may
this
handle
image.
only 30 segments in a while. So flow control means sender should not send too many or at such a speed that receiver cannot handle the segments. There should be a speed matching between sender and the receiver. So matching the sending rate to the receiving application's drain rate, that is called as the flow control. Alright, so we have over here the explanation. Now, for example, suppose TCP receiver discards out of order segments, right? So, just like we did in the go back N protocol. So, let's assume that if some out of order segment has arrived, it discards it. So, now there is a spare room in the buffer, and how the received room size is calculated. Received buffer, whatever is the size, minus last byte received minus last byte read. This
Receiver control sender, so sender won't overflow receiver's buffer by transmitting too much too fast. Suppose TCP receiver suppose discard. Oh, okay, wait, hold on.
N protocol. Alright, so we have over here the explanation. Now, for example, suppose TCP receiver discards out of order segments, right? So, just like we did in the go back N protocol. So, let's assume that if some out of order segment has arrived, it discards it. So, now there is a spare room in the buffer, and how the received room size is calculated. Received buffer, whatever is the size, minus last byte received minus last byte read. This is how the formula is done. And receiver in the beginning, it advertises the size of its buffer, or we call it as the spare room, by including the value of the receive window in the segments. Sender limits unacknowledged data to the receive window. That means it guarantees that it will not full the buffer of the receiver. Alright, so that was about
Why did I feel like a reliable data transfer? I could have sworn this is principles of segment structure. Was that really the beginning of this? Hold on. Okay, I remember this, okay. And he took out the slides for reliable data transfer, okay. Because I guess this already went over it. Typical, like this. If he asks what's the typical default, it's 4096. I could remember this, but it's like a wild card ass question. TCP receiver advertiser free buffer. RWND. Wait a second. That was on the quiz, so it can get an out of. Alright, hold on. Let's go back. I feel like I missed
including the
something.
done, and receiver in the beginning, it advertises the size of its buffer, or we call it as the spare room, by including the value of the receive window in the segments. Sender limits unacknowledged data to the receive window. That means
Oh, that's what this is. RWND is receive window. I was wondering what the fuck.
it guarantees that it will not full the buffer of the receiver. Alright, so that was about the characteristics of the TCP. Now we move on to the next part, which is the principles of the congestion control.
Yeah, they basically just skipped over connection management, alright. Before exchange data, sender receiver handshake. Agree to establish each knowing the other will. Alright.
Congestion is there are too many things on the network, right? So there are too many sources sending too many data very fast, and it is not possible for the network to handle all those data. So in that case, what will happen? Some of the data will be dropped or it will be corrupted, just like you have experienced congestion on the road. So for example, if we have a road, the road is designed to handle, like for example, 5 cars at a particular time. Now consider a case when we have 500 cars on the road at a particular time. So cars will be moving very slowly because the road is quite narrow. So that is called as the congestion. So congestion means when too many sources, they are sending the data too fast for a network to handle, which becomes difficult for the network to handle. Congestion control
What?
is not related
I feel like she just repeated herself.
particular time. So cars will be moving very slowly because the road is quite narrow. So that is called as the congestion. So congestion means when too many sources, they are sending the data too fast for a network to handle, which becomes difficult for the network to handle. So congestion means when too many sources, they are sending the data too fast for a network to handle, which becomes difficult for the network to handle.
Oh, yeah, she said the same
Congestion
thing.
control is not related to the flow control. So what happens in this case, some of the packets will be lost or some of the packets will be delayed. So what happens during the congestion on the network? Either you will take too much time to reach to your destination, or you will change your route. So that means the packet is lost or you will not go anywhere. So it's one of the top 10 important problem in the computer network research.
That's
All
probably gonna
right,
be a
so we
question.
have two broad.
It's gonna be like, what's the top 10 computer program problem? And I'm gonna have to remember congestion control, congestion.
Approaches to handle the congestion control: end-to-end congestion and network assisted congestion. Now what is end-to-end congestion and what is network assisted congestion? Let's talk about. So let's talk about end-to-end congestion control. In end-to-end congestion control, the network layer does not provide any explicit support to the transport layer for the congestion control services. So there is no explicit feedback from the network layer regarding the congestion control. Network layer does not provide that there is congestion on the network, you should send less number of segments or something like this. Even the presence of congestion in the network must be inferred by the end systems. So it is the responsibility of the host to like sense about the congestion in the network based on the observed packet behavior. So if it is taking too long for the receiver to receive a packet, receiver can infer that there can be congestion on the network. Or if the sender is receiving duplicate acknowledgement or no acknowledgement within during the timeout period, sender can sense that there is a congestion in the network. So it is the responsibility of the end systems to infer the congestion on the network based on the observed based on the packet behavior. This approach is taken by TCP. So TCP must necessarily take this end-to-end approach towards the congestion control, because IP of the network layer does not provide any feedback to the end systems regarding the congestion control. So TCP segment loss or the acknowledgement loss or the duplicate acknowledgement is taken as the indication of the network congestion, and TCP decreases the size of the window accordingly. Next approach to handle is the network assisted congestion control. So as the name says, there is no network, there is no feedback from the network, but there will be a feedback from the network. So with the
What?
network assisted congestion control. So as the name says, there is no network, there is no feedback from the network, but there will be a feedback from the network.
I think the way she said it
So
was
with the network
wrong.
assisted congestion control, the network layer components, for example the routers, they provide the feedback to the sender regarding the state of the congestion on the network. Now this feedback can be in the form of the single bit indicating the congestion at a link, or it can be in the form of explicit rate. A sender should send at, and this approach is used in the ATM available bitrate congestion control. So this approach was also taken in the early IBM systems, and it was proposed for the TCP/IP networks. Alright, so let's now move ahead.
I feel like I miss.
It can be on the network. Now this feedback can be in the form of the single bit indicating the congestion at a link, or it can be in the form of explicit rate. A sender should send at, and this approach is used in the ATM available bitrate congestion control. So this approach was also taken in the early IBM systems, and it was proposed for the TCP/IP networks. Alright, so let's now move ahead. Let's talk more about the TCP congestion control here. So that was the two approaches that we can take for the handling the congestion control. Alright, so how does the TCP senders determine their sending rates, such as they don't uh, congest the network and at the same time make use of all the available bandwidth? So TCP answers both these questions, how it determines the sending rates. They don't congest the network, and at the same time it makes use of.
Yeah, like I feel like this is never talked about here. Hold on. AIMD. Is that a approach? Senders can increase sending rate until packet loss occurs, then decrease sending rate on lost event. Yeah, because if it goes too fast, then you can have packet loss, so you slow it down, it decreases that, right? Additive increase sending rate by one maximum segment race size every RTT until loss detected. I don't know if that's good. Multiplication. Cut sending rate in half at each loss event. Oh, is that what? Okay, if it's in half, then that's good. I think. So up here, if there's a loss, it cuts it in half. Sawtooth behavior probing for bandwidth. Sending rate cut in half. Detected by triple duplicate ACK. On loss detected by triple duplicate TCP Reno. Tahoe. AMD. What does this even stand for? Don't think it matters. Oh, it says it's an additive increase multiplicative. Okay, that's what it stands for. Multiplicative decrease. Detail sending rate is cut in half on loss detected by triple duplicate hack. Why is AMD? Distributed asynchronous algorithm has been shown to optimize congestion flow. Like this stuff, like I would not think would be on the exam, but to my knowledge, it probably is. So if he asks something about what's a type of TCP congestion control, I can say AIMD, additive increase multiplicative decrease. But there's another one too, right? Just end-to-end congestion control. So is this just TCP congestion control? Is this just in the principles? So end-to-end, no explicit feedback on end-to-end. And then this one, approaches towards control. Network assisted has direct feedback. Alright.
All the bandwidth or the bandwidth that is provided to the TCP for its transmission of the segments. TCP answers the first point here. Congestion of the network. So lost segment implies congestion. So TCP, the sending rate of the TCP, sender's rate should be decreased. So when the segment is lost. An acknowledged segment indicates that the network is delivering the sender segment to the receiver, so sender's rate can be increased. So this is how the TCP can adjust to the congestion rate of the network. Second is bandwidth. Now TCP's strategy for adjusting its transmission rate is to increase its rate in response to the arriving acknowledgement. So if the acknowledgement arrives quite earlier than the timeout period, that means within the half of the timeout.
Yeah, this stuff isn't even in my notes, so I don't know. But I did see, yeah, here, bandwidth probing. Probing for bandwidth. This might just be what this is. They just figured out a name for it.
Period or before the half. In acknowledgement, when so these are the sender and the receiver, what are the things required sender by that congestion on the send 4 bytes.
Yeah, I don't think I need to know this stuff.
Simply by the loss event or
3 mechanisms. Alright, let's go.
Low start and in the beginning should be slow. That means should be slow in sending the segments. or it should, after the timeout event occurs, it should be conservative. That means it should decrease the rate of the size of the congestion window. All right. Okay. So AIMD, we are going to talk about the first approach. Additive increase and multiplicative decrease. We are going to talk only about this approach. So this approach increases the transmission rate.
I know,
Transmission
okay.
rate is
She does talk about slow start.
window
Okay.
size, probing for a usable bandwidth, because at the same time TCP has to utilize the bandwidth at the full rate until the loss occurs. So additive increase the congestion window by one maximum segment size every RTT. So for example, first send only one segment, then 2, then 3, then 4. This is additive increase, right? We are increasing the size of the congestion window. Multiplicative decrease, cut the congestion window in half after the loss. If loss occurs, cut the size of the congestion window in half. For example, first segment is sent, then second, then third, then fourth, then 5, then 6. So the size of the congestion window is like 6. Now for example, at this time, the size of the timeout event occurs, so it will cut the size of the congestion window to half at this point, that is 3. So for example, if it is starting sending additive increase in the increase, and if it occurs like for example congestion here, it's a multiplicative decrease. At this point, for example, the size was like congestion window 16 bytes. So at this point the timeout event occurs. So if you see over here, the congestion window is reduced to half, which is 8. So again, when it starts,
Trying to think. So there's end-to-end congestion control, and then what's the other one? Oh my god. End-to-end. Which doesn't give direct feedback. Oh my god, I go. Network assisted. Okay. I thought it's network something, but network assisted provides direct feedback. May indicate congestion level or explicitly says sending. Congestion inferred from observed loss. End to end. From observed loss. Or set sending rate. Okay. Network assisted control. End to end. Network assisted control.
sending linearly, it is increased. At this point, if the timeout occurs, it is the congestion window size is reduced to half. So this is the approach of additive increase, multiplicative decrease. Okay. So slow start. What is slow start? Slow start means it starts
One maximum segment size when loss detected by timeout. Optimize yeah, that might be a question right here. Why AIMD? Optimize congested flow rate network. Ooh. Have desirable stability. Stability, I mean. Stability. So let me think real quick. End to end infers on the loss, and it doesn't provide direct feedback. That's end to end. What's this network control? Congestion control. And then there's network assisted control, which provides feedback and then sets a rate, a congestion rate, I think. Mm. Then additive increase, multiplicative decrease is optimize congestion flow rates network wide, have desirable stability.
The congestion window by 1 MSS, one maximum size segment. So for example, let's consider over here MSS is 500 and RTT is 200 milliseconds. So it will measure the initial rate, how to utilize the bandwidth. And how to utilize the bandwidth, we have over here the sending rate should be in the bytes per second, congestion window by RTT. So we can calculate over here the size of the congestion window divided by RTT. Congestion window will be calculated by MSS. We will convert this MSS into, because it is bytes, we will convert it into kilobytes. So 500 divided by 1000.
Connection begins to increase. Begins increase rate exponentially until first loss. One, two, four, and then
Will make it 0.5 kb, right? And RTT is 200 milliseconds. We will convert it into milliseconds, seconds. So 200 divided by 1000, because in a millisecond there are 10 to raised to the power minus 3 seconds. So it will be 0.2 seconds. So we can calculate the sending rate. Sending rate is 0.5 divided by 0.2, which is 2.5 kilobits per second, and it can be rounded off to 20 kilobits per second, right? So it can ramp up to respectable rate of 20 kilobits per second. So available bandwidth should be greater than this MSS divided by RT, which is the sending rate. So it is desirable to quickly ramp up to the.
it says check out the. Yeah, there is a congestion window here. Do that after.
Respectable rate, and when the connection begins, increase the rate exponentially fast until the first loss event. So in the beginning, increase the rate exponentially, but after the first loss event, decrease it. So with the slow start, for example, when the connection begins, increase the rate exponentially. So for example, it sends first segment, receives the acknowledgement. In the next RTT time, this is the RTT time. So segment received and the acknowledgement received is 1 RTT. So then it sends 2 segments. So because it receives the 2 acknowledgements for the 2 segments sends in the RTT, it next sends the 4 segments. So if the 4 acknowledgements are received within the RTT, it sends the 8 segments, right? So it increases the transmission rate exponentially until the first loss event. So double the congestion window every RTT. If you see, every RTT, the congestion size window is doubled. So done by incrementing the congestion window for every acknowledgement. Initial rate is slow, but it ramps up to exponentially very fast. Alright, so in this case, if the timeout or the loss occurs after 3 duplicate acknowledgements, I'm talking about slow start. After 3 duplicate acknowledgements, congestion window is cut to half, and then the window grows linearly. So if
Why does it?
there is a loss How does the loss occurs? Either by 3 duplicate acknowledgements. So if the 3 duplicate acknowledgements are received, then congestion window is cut to half and congestion window size after that will grow linearly. But if there is a timeout event, in case of timeout event is during that round trip time this acknowledgement is not received, right? So this is called as timeout event. In this case, congestion window, instead it will set to 1 MSS. It will not be cut to half, it will be set to 1 MSS, and then window will grow exponentially to a threshold value, and then
Why does timeout event seem... I don't know.
Grows linearly. So the philosophy is, if the 3 duplicate acknowledgements are received, it indicates network is capable of delivering some segments. Timeout is a more alarming event. So in this case, the congestion window is set to 1 MSS. So we have over here the refinement. When should the exponential increase switch to linear? When the congestion window gets half of its value before timeout. So if you see over here, in the slow start, let's go back. It increases exponentially, 1, 2 and 4. So if you see, first it sends 1 segment, then 2 segment, then 4 segments, then 8 segments, and maybe at this point the threshold has is received, and then it sends 2 2 again, because that was the threshold, so it sends 2 2 again. Now at this point it reaches. Now at this point, let's assume that there is either 3 duplicate acknowledgements received, or there is a timeout event. Now if the timeout event occurs, so in this case the congestion window size will be set to 1 MSS. If you see over here, if the timeout event, congestion window size is set to 1 MSS, and after that it will grow exponentially. So if you see over it, 1, 2, 4, 8 and...
Wait a second. Done. Initially congestion.
then it grows. But if at this point, let's assume that 3 duplicate acknowledgements are received, so in that
Loss event is set to 1/2 of congestion window before loss. So, what does that say? Congestion window in segments 8. We're on number 4. So 1/2 of that be 2, but then it goes to 5.
In that case, the
wait, it's talking about I'm not sure.
congestion window size is cut to half of the present congestion window size. So the present congestion, that it will, if you either sends 1 segment, then 2 segment, then 4 segments, then 8 segments, and maybe at this point the threshold has is received, and then it sends 2 2 again, because that was the threshold, so it sends 2 2 again. Now at this point it reaches. Now at this point, let's assume that there is either 3 duplicate acknowledgements received, or there is a timeout event. Now if the timeout event occurs, so in this case the congestion window size will be set to 1 MSS. If you see over here, if the timeout event, congestion window size is set to 1 MSS, and after that it will grow exponentially. So if you see over it, 1, 2, 4, 8, and then it grows. But if at this point let's assume that 3 duplicate acknowledgements are received. So in that case, the congestion window size is cut to half of the present congestion window size. So the present congestion window size is 12 and it will cut half, which is the 6. If we go back, size is 12.
Then it goes 4 to, okay.
And it will cut half, which is the 6. If we go back, it is cut in half. After that, it grows linearly. So if you see, now the window is growing linearly from 6 to 7, 7 to 8. Else the loss, the 3 increase 4 times. 4 is alright. So this was all about the chapter 3. We learned.
And then my professor has so much, wait, this is the end. Fairness goal of K, TCP sessions share same bottleneck link, each should have the average rate. TCP deployments often implement network assisted. Alright, we finished chapter 3, but hold on, let me stretch. Luffy with the gummy neck. Oh my god. Bro, what sucks is having to clean my room for the move back, or to go back to my house. So I gotta take apart this desk again. But we shall see. Alright, let me see. Hold on. So there's end-to-end congestion, which doesn't explicitly, was it? End-to-end doesn't. It doesn't directly, oh, was it feedback? It doesn't give you direct feedback. And then there's network assisted congestion, which gives you direct feedback. The other one infers, the end-to-end infers based off the packet loss or segment loss. I don't know. Let me see. Inferred from observed loss. So no explicit feedback. Explicit feedback. And then approach taken by TCP. That's crazy because the end here basically says TCP deployments often implement network assisted congestion. Am I reading that wrong? Congestion, a top 10 problem. Long delays and packet loss. Queuing in router buffers, buffer overflow at routers. Different from flow control. Informing too many sources, sending too much data transfer for network to handle, that's obvious. No direct or no explicit feedback from network, that's good. Congestion inferred from observed loss. Delay, approach taken by TCP. Routers indicate, or routers direct feedback, blah blah blah. And then the buffer control flow flow control. See, this part I'm so iffy about because I don't... Guarantees receive buffer will not overflow. Flow control, receiver controls sender, so sender won't overflow. Receiver's buffer by transmitting too much. See, there's something about this that I just can't process in my head for some reason. And look at this quiz again. The receiver includes receiver window value and TCP header. To free buffer space represents. Okay, yeah, so that is in this chapter. Okay. Free buffer space, that's here. See, if this was just a multiple choice exam, I would fucking ace it. Because looking at these now, I can... This one I'm still iffy about. With the selective repeat protocol, it is possible for the sender to receive an ACK. Still iffy about that, because the way that fast retransmits for three duplicates, three additional, triple duplicate, yeah. The sample, yeah, right here. Samples measured time from segment transmission until accuracy ignores retransmissions. And this thing changes because the average time is changing, so... And then, what else? So yeah, round trip time estimated is through the sample, which is the average, the segment transmission to accuracy, average several recent measurements, not just current. But I wonder how does it... if the first one never gets received, it just resends. But how do you determine the timeout for the first one if there is no previous ones? I don't know how that works. Do not know how that works. Been streaming for 3.5 hours of me studying. I think that's been good so far. I don't think I'm gonna do chapter 4 tonight. I think I'm gonna do like another 30 minutes of this chapter 3 and then do chapter 4 completely tomorrow night. And then I think I should be good. And then Tuesday night, I'll do a quick overview. Oh, you know what I forgot to do? I forgot to do these. Segment loss, trip timeout, congestion, and retransmission. What is this? Give the sequence numbers associated with the... Format your answer A, B, and C. Sequence. uh, format your answer as A, B, and C. So sequence numbers is going to be 404, and then it's first 5, which is 198. So 404 plus 198, 602. Uh-huh. And then this is going to be, is it 408 x, oh wait, no, it's going to be x 408 x x, and then this is 408 plus 198. Oh no, it's 404. Oh wait, no, I think this is gonna be 404 also here. Yeah. Let's go. Let's go. Let's do another one. Alright. 358 with 835. That's kind of annoying. 1193. 2028. 2863. 3698. Alright, so it's gonna go 358 x 358 x x 358. I'll try and get one that isn't. Alright, this is good. 94, and each one is 123. What is this? What is this? It's gonna be 94, and then I'm pretty sure the next one's gonna have the 123. So it's gonna be the 217 here. No? It's gonna be 94? Huh. Let's see if we could get one that... Oh, this one's too easy. 215 plus 730. Aha. So 215 did get received, so then... What? What? I'm confused here. If it's not that, then it's not that. The fuck is it? Packet 2 didn't go through. $9.45. How? What? That doesn't make sense. Oh, whoops, I forgot the comma. Alright, so it's gonna be x 420 xx 420. If that's correct, now I don't know how the other one was. Alright, so then if it's like this, maybe 115 plus 798. And then I'm going to just a guess 115 plus 798. Yeah, that's what I thought. What? 115 798. This doesn't make sense. What? 913 1. How does it? So if they're consecutive, they can go in order of 34. So this is gonna literally be then 369 704x. I don't know how. Alright. The deviation for the round trip time. Uh, I have no clue. Given the times, guess we do 1, 1, 2, 4. Wait, 2, 4. Uh, 8. Where and at which TCP can still start. Oh, I see. So it's gonna be 15.5, 16.5, 18.5, and then 19.5. Oh wait, Bro, what? What the hell's the threshold? Oh, it's right here. 1289. Given at which times this TCP is in congestion avoidance, I think it's at I putting 0.5, but it's not. Bro, I don't know how. Why are these so many? I don't think this is gonna be on the exam. Same with this. What is the sequence number of the segment sent at 1? It's gonna be 0. What? Oh wait, I didn't even read this. The sequence number is 118 every sequence number sent at T2. At T3. T4. I don't get the point of doing all of this here. What is the value of the ACK sent at T8? Is it gonna be 113? No. I think it's gonna be 0. Nope. 1. The delay is 7 time units, so the first segment received it at T8. There's gonna be 118 plus 838. There's gonna be 956. I get it now. What is the sequence number at T15? It's gonna be X. T16. It's gonna be X. No? Oh. Uh-huh. Oh, T16. Oh. Shit. Bro, I have no idea what the fuck I'm doing here. So 118 plus 838. T16 is coming from 9. So, do be 1794. Bro, what the fuck? Well, then I think it's gonna be 118. Isn't it gonna be cumulative ACK that gets sent? Assume there are no timeouts and out of order. Oh, so I think it's gonna be cumulative. So, wait, that'd be that then? It's cumulative. That's what it is. T19. I think it's X. What? So what is the sequence number sent? Would it be this? Oh my god. So yeah, TCP has cumulative acts. That's why we don't have this, because isn't this in UDP? Let me check. The NAC. Detect errors in transmitted segment. No frills, bare bones, Internet Transport Protocol. Why is there UDP? No connection establishment. It's simple, small header size, no congestion control. Oh my god. Let me think. The congestion control. There's end-to-end congestion control. There's no explicit feedback, and it's based off. Let me think. What's it based off It's based on the loss, the error loss. I think that's all it is. It's based off of that. And then, what's the other one? Connection, network assisted congestion control. No, network assisted control. There's explicit, what's it called? Feedback, explicit feedback. And there's, sets the, was it? It sets like the congestion intake something. Let me see. Do, do, do. What is flow control? Receiver control senders. And this is the free buffer space, pretty much. Yeah, and the advertises free buffer space. TCP receiver advertises free buffer space. Yeah, and no exclusive feedback. Congestion inferred from observed loss. Congestion inferred from observed loss. Congestion inferred from. Alright. And then direct provides direct feedback. Direct feedback may explicitly may indicate congestion level. Bro, why are they playing instruments out there? May indicate. Oh, wait. Next semester I won't have the same roommates. Let's go. I sure hope they're different. I sure hope so. And I hope they're quiet. Multiplicative decrease. How are your studies doing, Tristan? It's been about an hour and a half. I think I'm almost done, but just kind of trying to. What was this? Did I? Oh, this is annoying as hell. That was easy. Was the D? Was the? Hold on. Was it DHCIM or something? that in this chapter? Connection-oriented demultiplexing. Demultiplexing uses destination port only. Demultiplexing using 4 tuples, source, destination IP addresses, and port numbers. Okay. Happens at all layers. Why is there UDP? Simple, no congestion control. I'm pretty sure one question might be like a free response, and it might say, what's the difference between TCP and UDP? And that's gonna probably be like a 10-point question. And I think, what? Best effort service. UDP segments may be lost. It's connectionless. UDP checksum, detect errors, internet. I don't know if these are the same. I need to ask him. These mean anything. Internet checksum and UDP checksum. Internet checksum. If he doesn't give us the decimal numbers for this, it's gonna be pain. If there's a question like this. If he gives us the decimal numbers, it's free. I can do it easily. No frills, UDPS, it's pluses. No setup handshaking needed. Can function when network service is compromised, helps with reliability. Anything on the reliability of data transfer, I'm gonna be completely blank. Except this part, like it doesn't know what it's saying on the other side, basically. Unless communicated via a message. Complexity will depend on the characteristics of underlying channel. Sender retransmits. If it gets 3 duplicate, it does fast retransmit. Where I'm pretty sure fast retransmit it just sends all of them again. Let me see. Where did where the fuck's fast retransmit? I now I think now I understand where this I think R stands for the rate, which is this, and then I don't know what this stands for, the L. Yeah, go back in GBN. Basically is for don't buffer or can discard or don't buffer or buffer. What does that mean? What? I don't get it. This basically confirms sending it in order, but it can receive it out of order. Round trip time, I understand that. It's basically measure time from segment transmission to until accuracy. Oh, here, yeah. The sender receives 3 additional acts. Resend to unact segment with smallest likely that unact segment. But does it send cumulative? It doesn't. But these are ignored, right? Yeah, 3 duplicates. Lost segment is likely, so retransmit. Alright. Guarantees receive buffer will not overflow. Sender limits amount of unact data to received window. The fuck? A fin. It's just called end, end, end. I gotta call it end to end. Congestion inferred from observed loss. Delay. Observed loss. Inferred. Why is this red? This is what bothers me. Why is this red? Congestion inferred from observed loss. Approaches towards congestion control, network assisted congestion control. Provides direct feedback. I think I just need from network. No explicit feedback from network. Provides direct feedback through congested router. And then this, the AIMD. This one, I don't know why this. Why did it, I don't know. Optimize congested flow rates network-wide. Have desirable stability. Been optimized congested flow rates network-wide. Stability properties desirable. Yeah, I'm gonna make a meme. Hold on. I'm gonna make a meme. What the hell? Do 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 do. How do I change this font size? Is there a way to change this font size? Oh, there is. Hey, fuck this. I'm gonna just do this. I'm making a meme. Oh, wait, it didn't crop properly. Fuck. Look at it. Because UDP is connectionless. I've been wanting to make that meme for a minute. 'cause I'm a memer. Alright, yeah, I'm done. I'll be back tomorrow. Do chapter 4. I don't know when I'll start, probably tomorrow night. But we can do chapter 4. Same thing. Yeah.